Good afternoon, all. It's my pleasure to introduce our great speaker today, Professor Kamanio Chattopadhyay from Indian Institute of Sciences, Bangalore, India. And he is very well known in India as well as worldwide as a great metallurgist. In a research career spanning 50 years, Professor Chattopadhyay obtained his PhD from metallurgical engineering at Banaras Hindu University, and later he joined the faculty at Banaras Hindu University in 1975, and then moved to Indian Institute of Sciences in 1983. A professor of materials engineering, he served the institute in various positions. Currently, he occupies the National Science Chair, only the third engineer in the country to be bestowed with this honor. Professor Chattopadhyay, thank you for your time, and floor is yours.
I will be talking about aluminum superalloys for high strength, high temperature applications. Basically, a transition of a legacy alloys to an exciting future. We all know aluminum is atomic number 13 and the atomic weight is 26.982. I have to tell that because I'm talking about aluminum. And it is discovered by Hans Ørsted in 1825. Incidentally, this is the most modern element discovered which is used as a structural material. All others, starting from iron, copper, zinc, nickel, they are all discovered in antiquity, and only two other elements discovered recent time are titanium and magnesium. That is actually in the 1 century earlier than discovery of aluminum. So it is really a very new alloys, new elements, and with a melting point of 660.3 and density 2.7 grams per cc. And that's the reason it is widely adopted very quickly. And it is adopted everywhere, aerospace, the rockets, car, engines. So I think I don't have to talk about this audience about use of aluminum and its alloys. But it is also replacing copper as a conducting material. If one talks about aluminum and aluminum alloys, one cannot help but remembering these two gentlemen. Remember the contributions of Charles Martin Hall and Paul Herold. But their discovery was in 1886, and that is what Hall-Herold cell, which made it possible for aluminum to be used in a mass scale. And this technology has not changed much, even today. There is no other process which is actually adopted for the extraction of aluminum. Nevertheless, aluminum as a structural material owes its origin due to a accidental discovery by Alfred Wilms, a Prussian metallurgist. He discovered it in 1903, got the alloy cast and in a Friday, and without looking at it, he left to meet his girlfriend and returned on Monday. And in Monday, when he did a hardness test, he found that there is a dramatic increase in hardness. And that is how this age hardening of aluminum alloys begin, and that is how the story of duralumin, the first aluminum alloys, started. Now, before we go to the aluminum alloy, the classical aluminum alloys, because I thought I'll talk about some basics before I go to the why we wanted to go to high temperature and how we can go to the high temperature. Any strength of any materials is controlled by cohesive energy, and you can have a ball and spring model. There's a repulsive energy and attractive energy. And this strength, actually, theoretical strength of all these elements actually are very high. And the reason we don't get it is because of defects. We know that it is because of dislocations. It never achieves its actual strength. It deforms much earlier. So question is that how can I stop defects? motion and primarily the dislocation motion. Of course, the easiest way is to stop it by grain boundary, because two grains are in different orientations. And so if dislocation cannot move through grain boundary easily, so if we do the fine grain, it gets strengthened, and that is the normal strengthening procedure of aluminum alloys. You make it finer grain size, and then Hall-Petz equation comes in and you get a yield. We also have what is known as a solid solution strengthening. And today you can see the atoms in solid solution, the bright spots in it is an aluminum solid solution image, and you can see the bright spots which is the solutes. And dislocation has a difficulty passing through it because there is a strain around this because of the size misfit with the matrix atoms, and therefore it gets a barrier for motions and therefore strengthen. But most common strengthening is precipitation strengthening. And this strengthening depends on the size. If it is a small size, then it is quite effective to stop dislocations. And the equation in that you see in the slide gives you what is the shear stress required to cut these particles. And if particles become very big, the R1, of course, you have a R1 looping, and the dislocation can go around it and move together. Brings us to the edge hardening behavior. And we all know that I'll talk from now onward mainly aluminum copper alloys. And we know that maximum strength that we can get by edge hardening is about yield strength is about 300 MPa that one can get by simple edge hardening. And aluminum copper alloys, there's many precipitate, but all are plate shaped. As you see in the left hand side, that it is a metastable phase diagrams. You can get a GP zone, theta double prime, theta prime, and theta solvers with the increasing solvers temperature. Therefore, one should be able to get a high temperature strength in the aluminum alloys. But it does not happen. The reason it does not happen is because as we increase the temperature, rapid coarsening of the precipitate takes place and strength drops. And this is what happens. This is the aluminum copper alloys, and you can see plate shaped theta double prime precipitates. And if you put it at 300 degrees centigrade for 50 hours, then it dramatically coarsens and it has no hardening effect. The strength becomes almost like a pure aluminum. How can I get a high temperature aluminum alloys which works at a reasonably high temperature in the context of 600 degrees centigrade of aluminum melting point? There is a series of papers by Sidman where he used scandium ordered phase and hoping that L3HCl12 phase probably can replicate the superalloys gamma prime. Although it did not happen that, but that started the thought process. In 2010, a Boeing team visited us. They wanted to have a collaboration with Indian Institute of Science. As a part of big collaboration, they have a Boeing center, and they wanted to have a first Boeing center outside United States. And they came here. That time I was the dean, and I was part of the negotiation team. When everything was done, Shankaran, the Laird and Shankaran frame, and that time Shankaran was one of the main scientists in the Boeing, he turned to me and said, Kamanio, can we make a alloy which has a 250 megapascal strength at 250 degrees centigrade and going further 300 megapascal strength at 300 degrees centigrade. My spontaneous answer was, it's not possible. Many people have tried and it is not possible. Then he said, why don't you try? And that is how we started working on high temperature alloys. The question that we ask is that what can we do to stop coarsening process, and so that the precipitates in aluminum copper alloys, we started with aluminum copper, theta prime and theta double prime, particularly those two alloys which have a solvent temperature pretty high, will not coarsen and still strengthen the alloy. So what came to our mind is, one, what Sidman was doing in scandium, and second, can we do a controlled segregation? When I looked at the ordered precipitate, these are the elements, all of them can produce ordered phase, but except scandium, all of them are metastable. The stable phases with all these elements are either DO22 or DO23. So we decided that let us look at these elements and what we can do. But the problem is, we started with zirconium and hafnium. But one of the first problem we encountered is that if you add hafnium to aluminum, it produces a cellular precipitate. This is one of the microstructure we obtained, which I like very much. It shows the cellular precipitation from a grain boundary, and also the coarsening of what is known as a cellular coarsening of those cellular precipitates. And we all know the moment these precipitates of this morphology appears, the aluminum, the strength goes to very low value because it fractures at the boundaries. For aluminum hafnium, if you add silicon, cellular precipitation can be stopped. And what you see in the left-hand portions of the slide is that if it is a hafnium alloys with a silicon addition, you can see that ordered precipitates at the bottom with the image of silicon map and hafnium map, and it is really a good dispersions. And this precipitate is, you can see right hand side, you can see the micro hardness, and you see that hardness is at 450 and 400 degrees centigrade, pretty stable over 100 hours. That means this is like a gamma prime in nickel-based superalloy. This is a very stable precipitate. Unfortunately, however, you cannot have a large volume fraction. That you can see from this diagram. This is same thing, zirconium, and small amount of niobium is added to stop the cellular precipitation so that you get a homogeneous L3X L12 precipitate. The volume fraction is low because of the phase diagram. Even if you take metastable L12 solvers, it is very near to the pure aluminum site, and therefore you cannot have a large volume fraction of the precipitate. And if you do not get a large volume fraction of a precipitate, you cannot increase its strength. Though it is high temperature stable, it is coherent and everything, these really cannot use as only precipitate to strengthen the aluminum alloys. So what can I do? We can use it as a part of our efforts, but we have to do something else. What we decide that we'll do a controlled segregation of the precipitate interface so that segregates stop coarsening. Of course, segregation at aluminum copper interface is well known for last about 15 years. The time we started work, there are work again in the Sidman and Dunan's group where they have shown that copper can segregate at the interface. And basically what happens is that this is a precipitate of theta double prime, theta prime, and at the growth interface, this is semi-coherent and broad face is coherent. And immediately you can see that there's a change in interfacial energy as a function of compositions, depending upon the nature of the coherency, and interfacial energy decreases with the solute concentrations for a incoherent, semi-coherent interface far greater than a coherent interface, mainly because segregation is larger in those interfaces. Therefore, we decided that we'll combine both. We'll combine the precipitation, theta prime and theta double prime precipitates, and the ordered precipitate to strengthen the matrix and produce an alloy, which hopefully will meet our goal. So we devised a heat treatment cycle. We call it a three-stage heat treatment schedule. We took aluminum to copper atom percent, and then add 0.1 niobium and 0.15 zirconium to get a L12 precipitate, ordered precipitate of niobium and zirconium. The schedule is we arc melted and chill cast the alloy, then age only for 10 hours at 400 degrees centigrade. This is still the cast structure, and when after 400 degrees centigrade 10 hours, we precipitate out the ordered precipitate, and then we upquench it to solutionize. I'll show you what happens when you do upquench. And then, of course, classically age it, and aluminum copper alloys normally age at 190, so that we have done. This is the microstructure. As you can see left, it is the cast microstructure, and 400 degrees centigrade 10 hours, lot of segregate disappears even at this temperature. But if you do a TM, you can see that matrix is full of L12 precipitate, L3 that you can see from the inset diffraction pattern. We have also confirmed it by APT, and you can see the nice precipitate of L12 and comes out. After this, we upquench 535 degrees centigrade. We upquench because the segregate that you see at 400 degrees centigrade 10 hours, the left-hand side, they are all aluminum precipitate, copper segregations, sorry. Okay, so we want to get rid of this. So we do 30 minutes, 535 degrees centigrade, and they vanishes. Basically, all the copper segregation goes away, but the ordered precipitate does not go away. As you can see downstairs, down picture, and even APT, we find that, in fact, they remain as they were after the heat treatment. So this shows you what happens now if I age it. At 190 degrees centigrade, at lower temperature, give a aging treatment. Pre-existing L3Z and NBL precipitates act as a heterogeneous precipitation site. And that nucleates both theta prime and theta double prime precipitates. And that the right-hand side, diffraction evidence of these two precipitates are shown. This is what you see in the microstructures, that all these plate-like precipitates are nucleated on L12 precipitates, and they are basically the aluminum copper precipitate. You only see the theta prime, which consists of aluminum and copper, and the matrix only contains L12 precipitate. Therefore, we can inherit the distribution of the ordered precipitate distributions at high temperature to have the similar distributions at lower temperature aging, because every plate has nucleated on these precipitates of order precipitate. Every theta prime and theta double prime precipitates have nucleated on this. Therefore, you get a very fine distributions. And unfortunately, I don't think I can show you this, the 3D, but you can see that there's a plate. Down, you can see that the plate, that all the variants of theta double prime and theta prime nucleates on the pre-existing aluminum copper. So this is the microstructure evolution you see. Left-hand side, you can see that our alloy, aluminum 2 copper plus niobium zirconium, we inherit very fine distributions. Even at 250 degrees centigrade, 50 hours, they do not coarsen. 300 degrees centigrade, it coarsens. You can see the scale, but not as large as comparable aluminum to copper precipitate, which is given there. Simulations shows that this is phase field simulations and shows that aluminum copper coarsens very fast, but the aluminum copper niobium zirconium is very sluggish. It doesn't coarsen. Therefore, it retains strength. And this is the comparison. I think I should show this stress strain diagram. Hopefully, you can see a part of it. And you can see that tensile strength of aluminum, copper, niobium, zirconium is very high, whereas aluminum to copper is hardened, it is much, much lower at 250 degrees centigrade. Room temperature, they are not very different. Still, AC and Z, that is our alloy, is still very high compared to the 2024. But high temperature strength of our alloy actually surpass the 7075 alloys. So we are very close to what challenge Boeing had given us, that 250 megapascal at 250 degrees centigrade. We almost reached there, but after 5 years of the project started. So in between, Boeing closed the project, but left the money for us to do that. And therefore, we could do this. That's why I am grateful to Boeing, because they would have taken the money. We could not have achieved this. We also looked at creep strength at 250 degrees centigrade. And when you look at the creep strength of these alloys, they're pretty good. Aluminum copper zirconium itself is good, but aluminum copper niobium zirconium, the minimum strain rate is at 250 centigrade, is as a function of stress, is quite low, and therefore it is quite attractive as an alloy development. Let us now replace niobium with tantalum. Why tantalum? Because we thought that niobium and zirconium probably stopping the segregations, because zirconium and niobium diffuse very slowly in the aluminum matrix. Therefore, these alloys do not coarsen. And we thought that if we add tantalum, that will be even faster, even slower. So probably we'll get a better effect with a small amount of tantalum. And L3TA also is an ordered precipitate. So we added 0.15 tantalum with a 0.15 zirconium. And of course, the addition of tantalum, it still produces the ordered phase. And the top, you can see that L3Z are this ordered compound with the atomic columns clearly shown. If you do look at the diffraction pattern after the heat treatment, and you see that we actually get a very dense precipitate, and we get both theta double prime and theta prime together with L12 in the alloy. So tantalum additions actually enhances the distributions. And if you look at the micro harness to see both stability as well as the strength. It is a reflection of a strength also. Then you can see the tantalum additions. Microhardness profile is very stable, and the microhardness VHN is quite high, 150 plus. And one interesting thing that you see is that tantalum, zirconium is segregating only in the ordered precipitate, but tantalum is segregating both at the theta double prime and theta prime particles and their interface, as well as it is going to the ordered particles. So we looked at it in the slightly more detail, and we wanted to know which one is more predominant, the theta double prime or theta prime. As you can see, it is in TM, it is always difficult to find out which is theta double prime and which is theta prime, particularly in a high resolution HADIF. But we have solved that problem. Actually, if one does carefully HADIF, you can see that this left-hand side, what you see, it is the theta double prime, and right-hand side, what you see is the theta prime. So it is distinct. So one can find out what we are getting, and they map very well with that, their crystal structure and composition. The composition of theta double prime is L3Cu, whereas composition of a theta prime plate is L2Cu. So they are compositionally different, but both of these precipitate nucleate and an ordered L12 precipitate. So we decided to look at what about the segregations at the interface, because HADIF gives a Z contrast, so we should be able to get an idea. So you can see a precipitate. This is a theta prime HADIF mode, and you can see that there's a bright column at the interface. And this bright column, if you trace, you can see that there's a segregation because only interface is brighter. Inside it is not so bright. And we assumed, we'll prove later, that these are actually the segregation of, combined segregation of zirconium and tantalum. At this point, our microscope could not do a use which can resolve the column of zirconium and tantalum. So we must say that it is either mixed of zirconium and tantalum. But one more interesting thing that we observed, that when you look at these plates, for example here, you see they are not straight line. Plates are not going straight. This is a bit of a zigzag, and one plate sitting on top of another plate in the lengthening directions, slightly displaced. And this is more clearly shown here, that arrow, the down arrow, shows the displacement, which means this plate growth stopped. And then a new plate nucleated on the leading growth edge. This is well known in the precipitation literature as a sympathetic nucleations. So what is happening, that plate growth stopped for some reasons, but the driving force for the precipitation is still high. So a new plate nucleate at the tip. And that is how the growth proceeds. And if you look at the tip, you can see clearly a row of bright atoms, bright columns. That means that tantalum or zirconium is segregated on the tip, stopping the growth, and therefore a new plate has to nucleate to continue the growth. But this is not a proof, because Z contrast that we can do at that time, about 5 years back, cannot resolve the composition of the column. Today, probably in another 1 year, we should be able to do with the microscope working well with the yields. But so we have gone to APT. And this is the atom probe tomograph of this plate growth. This is the, you can see the slice in the D, mark D. That is the plate. And this is a 2D map. And if you look at the 2D map of copper, tantalum, and zirconium at the interface, the dark lines at the interface, you can see that tantalum is only segregating at the tip, whereas zirconium is segregating both on the tip and on the broad face. That means this is a tantalum which is responsible for the growth, stopping the growth of theta prime precipitate. And that is how we can get very high strength. We looked at the coarsening rate of these plates with the tantalum. And you can see that they are virtually very little coarsening with time. These actual experimental measurements, whereas aluminum copper alloys coarsen very rapidly. And because of that, this coarsening stopping is because of, now we conclusively prove that it is because of tantalum segregations at the tip, growth tip of the plates. And because of this, you get a very high strength at room temperature. Room temperature strength is actually more than 600, yield strength is more than 500 megapascal. But 250 degrees centigrade itself, you get more than 250 megapascal strength. And it has a reasonable ductility. So we concluded that tantalum addition can produce a very good high temperature aluminum alloys together with, of course, zirconium. So we looked at also the other refractory element that we can get. And you have seen earlier, I have talked about hafnium. Hafnium also does the same thing. It actually stops the coarsening very dramatically in aluminum copper. And since it stopped it, why it stopped? In this case of hafnium, we can do some segregation energy calculations. And you can see that at the aluminum matrix side of the interface, there's a tendency, segregation energy of hafnium is negative. So hafnium will tend to segregate in those layers, layer marked by 1 and 0, whereas other elements don't segregate there. To prove this point, we therefore again did a imaging of the tip of a growing aluminum copper hafnium silicon plate. And here you can see hafnium has a high atomic number. So zirconium has segregated at the broad interface, but you see very bright atoms at the tip. And this is a hafnium, which is stopping its growth, lengthening, and therefore it does not coarsen at all. And as a result, you get very high strength, even at 250 degrees centigrade, close to 250, but it is not as good as tantalum. So we think that tantalum is the alloying additions at the moment, which is probably the best, together with zirconium. Of course, the story does not stop here. There are other alloying elements, and there are other groups, particularly Oakley's group, which started working on this on this theme 9 years back, after we have started this, and Sidman and Dunan's group has done quite a bit of work, particularly on creep. But they have shown that manganese is another element which dramatically improves the high temperature properties of these alloys. So I think although we started this aluminum superalloy back in 2010 when we started the work, and Sidman about 2008 to 10 published a lot of work on scandium, I think the field is open now, and I think many other alloying elements probably will come, microalloying additions, which will enhance the segregation energy, it's a segregation behavior by reducing the segregation energy, and therefore a new era probably will open up for high temperature aluminum alloys. So thank you very much.
Thank you, Professor Chattopadhyay. It's a nice talk with a lot of excellent teamwork.
So I thought that was a fascinating lecture because I'm not an aluminium specialist. But there's one question. In the nickel-based superalloys, we have more than 70% of the gamma prime, the L12 order. Is there any possibility of making your aluminium hafnium system have 70% of Al3HF?
No, my answer is very clear. I have told earlier also that L3ZR, L3HF, L3TA, they are all product of an initial peritectic reaction at a very aluminum-rich area. So even Lever's rule does not, in a metastable phase diagram, tells you there's a limit of volume fractions of the ordered precipitator that you can get. That's why you have to get back into segregations and theta double prime as a strengthening precipitate and stopping is coarsening. Unlike nickel or cobalt, which, as you know, I worked on cobalt, where it is a gamma prime strengthening.
But supposing that we get rid of the copper and we just have aluminum and hafnium, is it possible to get a system where you have 70%?
We tried that. We tried that. Aluminum, niobium, zirconium, aluminum, hafnium, silicon. Strength is very low.
Okay. Thank you.
Professor Suresh Babu left because of some other meeting, but he asked a question. Before that, he said that it's a quite interesting talk in the new direction of aluminum-based superalloys. His question is, the stress strain diagram looks like that of titanium alloy with less strain hardening after yield stress. Are there any fundamental reason for this?
See, we have not really looked at both creep and stress strain. They are rudimentary. And we should do that. You see, we are excited on how to design alloys. So we have not really looked at the mechanical properties and particularly creep and fatigue that carefully. Only recently I asked my colleague Surinder Makinen, who is now he was my student who started this work, but he is now my faculty, and he has large group. I'm a emeritus professor. I cannot have a large group. So I asked him that let us start looking at the strength of this, the classical yield strength and ductility, as well as the creep properties of these materials. I think we'll be able to do it soon. But yes, it looks very, very similar to titanium alloys, particularly high temperature, because high temperature I think it is edge hardening, the work hardening is not playing a big role in the matrix. That is why titanium also, because there is not a very large work hardening. And here also there may not be a very large work hardness.
There is a lot of work also happening in the direction of aluminum cerium based alloys, right? Do you think that would be a possible alternative?
I last 5 years I did a lot of work on cerium. I have not published yet, partly because classical work on cerium, aluminum cerium, that people have done quite a bit, particularly people who work on cast aluminum alloys.
Yeah.
And companies which collaborated quite a bit with Dunan's group, and they have done quite a bit of work on those alloys. They did not, they looked at aluminum silicon cast alloy.
As an alternative to aluminum silicon for automotive. Yeah.
Yes. And therefore, what happens is that they didn't look at what is happening to aluminum 11 cerium 3. If you add scandium there, our normal thing says that this is line compound intermetallic, so nothing will happen in the intermetallic compound aluminum 11C3, but that's not true. And we are working both cast alloys, different kind of solidification behavior of this in collaboration with Penn State, because we need to access the synchrotron facilities. And one of my students is there today in Penn State, and the other in University of Penn, not Penn State. And what we have found that the story of intermetallic will publish very soon, but even if you look at the paper by the Chinese group, it is very clear the story of intermetallic is not over yet. They have shown scandium segregation inside. And they give a very fancy name to this. For me, the classical phase transformation school grew up. I never believed in those fancy name and fancy stories, but cerium is inside, scandium is inside cerium, and it produces a phase transformation. So hopefully we'll publish very soon. And then I think almost all these intermetallic L3, aluminum cerium, aluminum yttrium need to look at with a microadditions.
I thank Professor Chattopadhyay for his valuable time in providing this great lecture in a new direction of aluminum superalloys. And I hope you all also enjoyed. Thank you, Professor Chattopadhyay, and have a nice evening.